Okay, everyone, today we're going to continue our FRQ trainer with what we like to call the graph of the derivative problem. And in these graphs, you're going to be looking at the graphs of things which may not be written as a derivative at first, but as you delve deeper, you're going to find that the graph that you're given is in fact the graph of some derivative. So to help us here, we're going to have Mr. Cary Grant and the movie North by Northwest, which is probably, if you're only going to watch one or two Alfred Hitchcock movies, this is probably one of the ones you should watch. So we have North by Northwest, and I'm not going to read this entire thing to you, but it's basically the case of a mistaken identity. And we have Cary Grant, who in probably the most indelible part of the movie, he's chased by an airplane who's trying to gun him down somewhere in Indiana. And this is only important that he's in Indiana because he's the character Roger Thornhill is actually from New York, and through a series of circumstances finds himself in Indiana. So here we go with the actual part of the question. So let y be the crop duster's position along a north-south axis where positive values of y indicate position north of a crossroads. At t equals 0, the crop duster is at 20 feet north of the crossroads. At t equals 5, the crop duster's velocity is 15 feet per second. And I'm pretty sure that if you zoomed into that graph, you would see that that graph of the velocity at t equals 5, you would see 15. So here are the questions at letter A. Find the values of y prime of 5 and y double prime of 5. And is the plane's velocity increasing or decreasing at t equals 5? B. How far does a crop duster fly in the first 10 minutes or first 10 seconds, and in what direction? C. Relative to the crossroads, what is the plane's north-south position at t equals 10? And D. Are there any intervals where the crop duster is traveling south with decreasing speed? If so, what is that interval? So let's take a look at letter A here. Okay, so we're here to find the values of y prime and y double prime at 5. So first of all, I like to think of this, velocity and position and acceleration as a chart somewhat like this, where if you go in one direction, the direction of the derivative, you get yourself from position to velocity to acceleration. And in the other direction, using an integral, you get from acceleration to velocity to position. So you're noticing that we're going to try to find y prime. And if y is position, then y prime is going to be velocity. Well, guess what? Velocity is the graph that they gave you. So you should be able to just read the graph and figure out what is v of 5. And actually, they tell you v of 5 right at the beginning of the problem. They tell you v of 5 is 15 feet per second. So therefore, y prime of 5 is also 15 feet per second. The next part's a little bit trickier. To find y double prime of 5, you need to find v prime of 5. Well, how can I get v prime from a graph of v? And if you remember, v prime, the derivative of v, is the same thing as the slope of the graph. Now we can go up and take a look at the slope of the graph. It's a straight line segment with negative slope, so we would expect to see v prime being negative. And you have this coordinate here, 10, 0, and this coordinate up here, 0, 30. Definitely difficult to read, but it is there, 0, 30, and 10, 0. So if I want to find the slope of the graph, I just need to use the slope formula. v5 is equal to v10 minus v0 over 10 minus 0, which is 0 minus 30 over 10 which is just -3. Units on that, I think we're looking at feet per second per second. So since velocity is positive and velocity prime is negative, that means the speed is decreasing when t equals 5. Whenever there's a disagreement between a quantity and the quantity's derivative, that means that that quantity, or the speed in this case, is decreasing. Moving on to letter B, how far does a crop duster fly in that first 10 seconds and in what direction? For this problem, how far does a crop duster fly? What you're really looking at is a change in what are we saying here? A change in position. Since a crop duster doesn't turn around, there is no distinction to be made between change in position and total distance traveled. So how do I get a change in position? Well, a change in position is just y10 minus y0. That's the change in position from t equals 0 to t equals 10. And if you look at that, that is the second half of the fundamental theorem of calculus, isn't it? That's a change in position. So let's just complete that with the other half of the fundamental theorem of calculus. Okay, that's equal to the integral from 0 to 10 of y prime. And what was y prime? Y prime is the velocity function. So we're bringing it back to the graph now because we have the graph of the velocity function. And using area, we should be able to figure out what that integral from 0 to 10 of velocity is. Let's peek up there and see if we can figure it out. From 0 to 10, we have this triangle. Here's t equals 0, here's t equal 10. So the area here between the curve and the x-axis is just the area of a triangle. The base of that triangle is from 0 to 10, which is 10. The height of that triangle is the height at the highest point, which is at t equals 0, and that height was 30. So there's my area formula for a triangle, 1/2 base times height. And then you're going to multiply that, you get 150. I'm going to note really carefully that that 150 is greater than 0, because changes that are positive here, positive means in the north direction, and negative would have meant in the south direction. So the crop duster is going to fly 150 feet north during those first 10 seconds. Now letter C is closely related to letter B because now we're trying to find that plane's north-south position at t equals 10. Well, we already figured out that we were using the fundamental theorem of calculus to find the change in position. So we're going to complete this problem, this part of the problem, just by using that fundamental theorem of calculus yet again. This time, taking a look at the left side, I have one known and one unknown. I know what the position was at t equals 0. It was given to me as 20. But I don't know the position at t equals 10. Now, a careful look at this fundamental theorem equation. We've got two knowns and one unknown, or just that one unknown. So plugging in the numbers, we knew that y0 was 20. We know the integral from our area calculations in part B was 150. And then it's pretty easy to solve for y10. y10 is 170. Since that's positive, I know that at t equals 10, therefore, that plane's position is 170 feet north of the crossroads. Now, letter D of this problem is actually a series of deductions that we're going to have to make. So are there any intervals where the crop duster is moving south with decreasing speed. So we're going to have to dissect what both of those things mean. So first of all, speed decreasing. What does that mean? Well, that has to mean that the velocity and the velocity prime have to disagree with each other. So velocity is greater than 0 and v prime is less than 0. That's one way to get decreasing speed. Or velocity is less than 0 and v prime is greater than 0. That's the other way to get decreasing speed. Now, only one of those is going to be applicable because we're taking a look. We want to also know when is the plane traveling south. And the train travels south only if the velocity is less than 0, which means the one that correctly applies to our situation is that second part. We're looking for an interval where velocity is less than 0 and v prime is greater than 0. Well, what do each of these mean for the graph? V being less than 0 means that we're looking for a bit of the graph that's below the x-axis. Because below the x-axis, of course, that means velocity is negative. Velocity prime being positive means that the slope of whichever part of the graph we're looking at is got to be positive. So is there any place below the axis where the slope is positive? I don't know. Let's take a look at the graph. Oh, right over there. In that yellow highlighted section, it's below the axis, first of all, and second of all, it has positive slope. So in that yellow highlighted section over there, that is a place where the velocity is negative, yet the slope of the velocity is positive. Or to summarize again, that is a place where the crop duster is moving south with decreasing speed from t between 13 and 24. So that's all of those questions that we had to deal with to get our mind going. Let's take a look at what's in the box here for our notes. And there are 5 things here, no real equations because you should know the fundamental theorem. And then all of those area formulas are all stuff from geometry. So I'm not going to sit here and tell you how to take the area of a triangle. That's, figure that part out on your own. So we need to interpret the graph as a derivative of something. It's very rare for the AP Calculus exam to give you a graph that's not a derivative. Okay, there are a few reasons for this, but you can pretty much take it on faith. If you're given a graph, it's the derivative of something. If the graph is a derivative of something, then the second derivative of that something is the slope of the graph, or derivative of the graph is just the slope of the graph. And if you look at yb minus ya, that's going to be the area between a and b. Anytime you need to integrate, if you need to evaluate an integral, that's going to be an area. And remember that not only is that an area, that's going to be equal to yb minus ya. There is that other thing to think about. Most of the time, the context here will be position, velocity, and acceleration. And then you're going to use the fundamental theorem on the velocity curve. If you use that, you're going to find displacement. And if you're given an initial position, then you can find a final position as well. Also, sometimes, if you're given the final position, you'll be able to find the initial position through pretty much the same process. Okay, so pause that if you need to take notes, and we're going to continue with the check your understanding. Here's our check your understanding. A car is traveling on a straight road. I used an airplane, they're using a car. Okay. For t equals 0 to t equals 24 seconds, velocity in meters per second is modeled by the piecewise function defined in the graph above. So that graph is a graph of the velocity, and they tell you so over here. Or if you think about it the way that I'm trying to get you to think about it, that is a graph of the derivative of position. Okay? I know that in your brain you're thinking, yeah, of course, the velocity is a derivative of position, but you really got to approach it as this is the derivative of something. So the first part, part A, find the integral from 0 to 24 of the velocity function. Use correct units to explain the meaning of that integral. Okay, so let's write down what we're supposed to figure out. That's that integral from 0 to 24 of vt. And remember what I said. This is a graph of someone's derivative. And the derivative that this is a graph of is, well, we don't have a name for it. Well, why don't we call it position? Also, if you need to integrate this, you're just going to find area. The integral of any graph is very, very, very much the same thing as area. So, what is the area of this graph? Well, I'm looking at it and it is a trapezoid. So it's 1/2 base 1 plus base 2 multiplied by height. If you'd like to turn this into two triangles and a rectangle, be my guest. It's not going to hurt anyone. But the most efficient way here is to look at this as a trapezoid. So let's fill in base 1, base 2, and the height. And now we're going to do some arithmetic. We get 360. And here, what I started off saying is that 360 is the position at 24 minus the position at 0. So the position at 24 minus position at 0, how do you interpret that? Well, that means that the car traveled 360 meters for t between 0 and 24. Or, if you prefer, it is the change in position from t equals 0 to t equals 24. Okay, part B here. For each v prime equals 4 and v prime equals 20, find the value or explain why it does not exist. V prime is the slope. So at the core here, you're just finding the slope. So let's look at t equals 4 and figure out what the slope is. I'm going to scroll up here a little bit. And at t equals 4, oh, look at that. At t equals 4, there is a corner. So does the derivative exist at a corner? No. Slope doesn't exist at a corner. So v prime of 4 doesn't exist as well, since v has a corner at t equals 4. Now that's not what's going to happen at t equals 20. You'll notice at t equals 20, right about here, we are at a nice smooth part of the graph. So we can find v prime of 20. V prime of 20 is just going to be the slope right here at t equals 20. And how do you find slope? Well, you use the slope formula. And you use the 2 points that you know the coordinates, or the 2 points that are closest. It's going to be the velocity at 24 minus the velocity at 16 over 24 minus 16. 0 minus 20 over 8, which is negative 20 over 8. Did you think I was going to simplify that or something? No, not necessary. And units here, that's feet per second per second. I strongly discourage you, as I always have, I strongly discourage you from writing this as feet per second squared. While that is a valid interpretation if we're talking about physics, we're talking about the change of the rate per second. So it is a change in the rate per second. Okay, everyone, that is what we have for you today. Hopefully this was a little helpful. I know this is mostly a calculus AB skill that we just went on. So, get your calculus AB grade up. And if you are in calculus AB, then good job. You're gonna get a 5. I just know it. All right, have a good day, everyone. We'll see you next time.